Welcome to CS270. I wanted to talk about Program 4. I've been getting some questions about that by email and on Canvas chat and Canvas message. So let me go through a little bit of it. Of course, with this being a major programming project, I'm not going to be giving you the solution or giving you my code for it, but I wanted to at least make sure people understand what you need to do, what the program needs to have, and where to get started. So our goal here is to write a shell. This is the program that you interact with in Unix that you type commands into. It executes those commands, maybe reports things back to you. So when you log into your computer or your virtual machine with PuTTY, for example, and you see something like this, this is the shell. I am interacting with the shell right now. This is the shell's prompt, actually including the $sign in the space, and whatever command I type in gets executed. Well, I have here my solution to program 4. I can run that. The prompt is much simpler here. We're not going to try to figure out what the current directory is and print that and so on, although we could. We're just going to print shell for the prompt. If you want to make that fancier, that would be fine. But in the shell, I can type in commands and they get executed. You'll notice there's a little bit different of a difference about how ls is executed. I don't get color when I run it within my shell. And that's because in bash, the shell that I'm usually interacting with, I have, and probably most of you have, an alias defined that makes ls actually run a more complicated command. If I exit my shell, type ls, then I can see when I run ls, it will actually run this. Your shell isn't going to implement aliases like that, so a few commands might look a little bit different, ls in particular. Going back into our shell, so one of the things that we can do, besides just executing a command, is redirect a command. You implemented most of the code you needed for this in Lab 3, and if you didn't finish Lab 3, do at least take a look at the Lab 3 video. That will walk you through everything you need for that, which will end up being a pretty substantial chunk of your code for Program 4. So let me do a redirection. Instead of doing ls just to standard out, I will redirect it to out.txt. Nothing came to standard out, but now if I run the command cat on out.txt to display that to the screen, I see the output. And if you remember from Lab 2 or the Lab 2 video, ls, when it's writing to a file or a pipe as opposed to a terminal, like it is here, when it's not writing to the screen, it will put each file on its own line. All right, so I can do ls, I can redirect. Another thing that your shell is going to need to implement is input redirection. Now, to be able to show you input redirection, I'm not going to be able to use ls. The program ls doesn't read anything. So let me use another program, tr. tr stands for transliterate. I give it a range of characters and another range of characters. It reads from standard in. So I'm typing hello, and every time it reads a line, it will apply the transliteration from the characters in the first list to the corresponding characters in the second list. So I type hello, it prints hello in all caps. I type world with an already capital W. The capital W didn't need to be changed, but the other 4 characters did, so I get world. The reason I'm showing you this program is it's one that does that reads from standard input and writes to standard output, what's called a filter in Unix terms. So we can see how that works with redirection in our shell. So in particular, I can do that command, but instead of taking input from standard in, I can redirect it from, well, let's say that out.txt file that we just created. And now I see the file transliterated, printed to standard out. I can also redirect both standard in and standard out. nothing showed up on the screen, but if I caps.txt, I've done the transliteration and written it to this file. There are a few other things your shell will need to support. One of them is the cd command. So there is an external command called pwd, which shows you your current directory. This isn't something that you need to implement. It's already there. Once you implement external commands, it can run ls. You could run this as well. But let me use cd. cd can't be implemented as an external command. And the reason is, in Unix, each process has its own current directory. When you create a child process, it inherits your current directory, but if the child process changes its own current directory, it doesn't affect the parent. Meaning, if cd were an external program, the child process would change its directory. It would now have a new current directory. Then the child process would exit. We're back in the parent, and once it waits for the child, and the parent's directory hasn't changed at all. So it wouldn't work. So cd has to be, in every shell, implemented as a built-in command, one that's interpreted by the shell itself. And my shell does have that implemented. I cd ... which means, if you remember from the file system chapter, the parent directory. I can type pwd now, running that external program that prints the current directory, and I'm, in fact, one directory up. I can also cd back to where I was, and if I run cd without any commands, or without any arguments rather, it puts me in my home directory. That's something that you will have to look up. There is another built-in command called setenv, but let me first show you what the environment looks like. This is a list of key equals value pairs that each process has a copy of. Process inherits from its parent, but changes made in the child or parent aren't reflected in the other. And it has information about my current shell, about options that I want to pass to certain programs by default. For example, I have an environment variable that says, how should ls color its output? Which file name should get which colors? I have one from SSH showing where my SSH connection is coming from. I have one from, this one is set probably somewhere system-wide, but it can be overridden by each user, that says what language should programs operate. The C language means don't do any translation. I could also have said EN_US there for American English. The .UTF-8 says that programs that are able to at least should produce output encoded as UTF-8 if there are special non-ASCII characters. Display is where things will show up when I run a graphical program on Unix under X, and so on. One in particular here is home, which is your home directory, user, which is your username. Programs, of course, shouldn't use user for security reason because we can change it. Let's see how. There is a shell, so there is a command that you will need to implement in your shell, setenv. This is different from how it works in bash, the shell that you're usually using. There you would write just something equals something. But here we have to use the setenv command. And I'll set env user to Mr. Hyde. Do the environment, and I can see that it has changed. The other thing that I can do is to remove an environment variable, and the way I do that is by running setenv with only one argument. And now, if I do env and I look between xdg session ID and pwd, it's not there anymore. The user environment variable has gone away. Finally, one last command is exit. It exits the shell. This isn't the only way to exit your shell. You should also be able to exit by sending an end of file. If you're typing into standard in, that would be Control D, but there are other ways as well. So that was not necessarily all that exciting, and this might not be exactly exciting either, but there is one more thing that we need to support. Let me remove those files that I made, and let me make a script for my shell. So a script is just a file with a list of commands to run. So that might be something like ls to out.txt, tr, lowercase to uppercase, from out.txt to caps.txt, rm, remove out.txt, and caps.txt. So this will do something similar to what we did before. It will run ls, send its output to a file out.txt, transliterate that from lowercase to uppercase, redirecting that to caps.txt, remove the out.txt, cat the caps.txt, so display it to the screen, and then we'll also remove caps.txt, so the script cleans up after itself. So I've named this capls.script, and I can run it with my shell, capls.script. And I see that output, which came from the cat command. I could maybe add a few more things in there to verify how it works. All right, so there is another program in the provided directory, run test. You'll have to have your shell implemented first to test it. But this will run a series of tests, reporting back success or failure. In this case, my shell succeeded on everything. We'll talk a little bit later about what failures look like. All right, so let me go instead of to my PA4 solution directory, to my PA4 provided directory, and we can see what you get, what you download from the assignment. So that includes a make file. You're welcome to change this make file as much as you want. It's currently set up to build your shell from a file called, if we look at objects, parser.o. That will be created from the file, one of the files that I've provided you, and shell.o, which will be something that you implement. Shell.o, at least the way that I've written it, the way I've written the make file here, will depend on shell.c, and there's a rule to convert C files to O files using GCC with these flags, -C to compile only and not link, specifying the output file, and so on. There's also a rule on how to build files, object files from C++ files using this CXX variable, which will turn into G++ and slightly different flags. So you're welcome to implement in either language. If you do implement in C++, remember to change this first line. Change the line that does the linking to use CXX. And then also remember that the things that are written in parser are still, parser.c are still C code. You're able to call those from C++. The header file is set up so that you can. But that does mean it takes a C string as an argument, for example. If you have a C++ string, you'll have to use the .c_str member function, for example. So the make file, you might have to make a few changes to if you're doing C++, but there won't be a lot of change here. If you decide to implement your program in more than just 2 source code files, then you might need to add those to objects and sources appropriately. All right, so let's leave the make file. Take a look at some of the other things. Run tests I already showed you. You shouldn't need to modify that at all. But if you want to look through it to see what it does, it's actually not terribly complicated. For each of the test files in the test directory, it prints a message, it runs your shell with that test file as input, redirecting the output and the errors. Then it compares the output to another file that's in the downloads with the expected output, prints a message if they're different, then checks standard error. If your program produced an error message and it shouldn't have, or it should have produced an error message and it didn't, that will be reported as a failure. Otherwise, it's success. All the stuff to implement that is in this test directory. There are a series of script files. These are the things your shell is being tested on. So if you find your program's failing a test, take a look at that script, figure out what it's supposed to be doing, and make sure that your script is actually doing that. Also, in test/expected are the expected output and expected error messages. Your shell's output has to match exactly. However, your shell's error messages don't have to match exactly. What we check is if you produced an error message and we didn't, that's a failure. If we produced an error message and you didn't, that's a failure. But if either we did and you did, whether it's the same message or not, or we didn't and you didn't, then your test passed. So if we look at all these .error files, -l, the ones that are 0 bytes are places where you shouldn't have produced an error. The ones that are more than 0 bytes are ones where you should have. So let's take a look at one of those tests just to see what's happening. So, well, let's take a look at the very first test, test.00.command.end. So all it does is run the echo command. Echo takes arguments on the command line, prints those to standard output, followed by a new line. So if we look at the expected output, so I have .error and .out. The expected output should be just that message, and the expected error should be nothing. Let's take a look at one where we do expect an error. How about CD failure? So that's test 18. Okay, so here we're trying to change to a directory that doesn't exist, which should fail. One of the specifications in the shell is if a built-in command fails, it shouldn't terminate the whole shell. It should be considered an error for that command, but you should keep going. Meaning our program should print still alive. It should also make an error message about the cd command not working. And if I look at the expected files, the expected output does have that still alive output, and the expected error includes something. Again, your error doesn't have to match this exactly, but it should be of the same general form. It should have something indicating the context of the error, what the user was trying to do, or what the program was trying to do that caused the error, and then the nature of the error, which you get from stir error or p error. The other thing that we have is parser.c and the associated header file shell.h. So parser.c has a couple of functions. Free command and parse command are the main ones, or the ones that you'll be using. There are a few other helper functions here. Notice they're defined as static, meaning you're not able to call them from outside this file, meaning you won't be calling the capital strdup or the alloc command functions. You should interact with it through parse command and free command. Parse command, well, rather than looking at the implementation, let's look at the header file, which has some more information. Parse command parses a command line, which we pass in as an argument. Notice this is a C string. So again, if you're working in C++, you might have to convert using the .cstr member. or a member function of the string class. But we have C string that has our command line. We will parse that. That is, break it up into command, arguments, redirections, and return a newly allocated structure. We'll take a look at the structure in a minute, representing that command. So we're returning a pointer to a struct command that was allocated dynamically, so we're also responsible as the user for, or as the caller, for freeing it eventually with the free command function. If there was a syntax error, if parse command just was not able to parse the command at all, which shouldn't happen, then it will call exit. It'll exit with the status of 127. So one place where that would happen is if you tried redirecting twice with the same kind of redirection, or if you provide too many arguments. There is a limit here, which is defined in the header file. Shell max args, a maximum of 30 arguments, including the program itself. So if it ends up being bigger than that, that's an error. The struct command itself has an array of character pointers, which are pointing to the arguments. That includes argument 0, the program itself, and arguments 1 through n, which are the additional command line arguments. So if I do ls-l, ls is args 0, -l is args 1. The array of arguments has a null pointer at the end as its last element to indicate that that's the end. This is in exactly the form that you need to pass to execve. So, or in the case of this program, execvp. So this is the thing that you would pass to, for example, your call redirected function that you implemented in Lab 3. There's also some additional information here. The input redirection, if there was any, null if there was not. So if I did ls greater than out.txt, in reader would be a pointer to a string that's out.txt. Likewise for the output redirection. If I didn't do that kind of redirection, the pointer will be null. Notice input and output redirections aren't arguments. They don't appear in this list because they're handled by the shell and not actually passed to the program directly. The program just knows about that or is affected by that by virtue of its standard out and standard error being pointed at those files. But that's set up by our program, by the shell. And then finally, free command, we pass it one of these struct commands and it deallocates everything. So in particular, this deallocates the command itself. So it assumes that was made with malloc, meaning after you call free command on a command pointer, you can't use that command again. It also frees all of the strings stored here because these strings, the input redirection file name, the arguments, and so on, were also all allocated using malloc. Okay, so that is what we have, or what we have to start with. So I wanted to, in the next video, talk a little bit about some of the specifications, and then in the video after that, how you might get started with programming. Thanks.